Hello guys, welcome to another episode of Sun Talk Show. So today we are going to code Wolfram language, a geometric inversion with a stereographic projection. Okay, so let's show my screen. So Wolfram language coding geometric inversion with stereographic projection. Now you are looking at geometric inversion. Now there's a relation between geometric inversion and stereographic projection. Now I'm going to explain all these, okay? And I did several videos on geometric inversions in the past, so you can search YouTube, you'll find it. So this will be about an hour, so you're gonna learn geometry and you're gonna learn Wolfram language coding, which is a term rewriting system, okay? It's a term rewriting system, fantastic. So here is today's talk show. So let me show you what is geometric inversion, okay? Show in browser. Now video check, audio check, okay, we are good to go. And the keyboard I'm using is the Expose today. Today I'm using Expose keyboard. Fantastic, okay, I recommend it. So back to, so let me show you what is stereographic projection. So here it is. We did a video on this one as well, live coding. So we coded stereographic projection. Here is the code. So let's start Wolfram language. Let me start Wolfram language and just show the code. Okay, so if you have comments and questions, post it. Okay, I love to see your comments and questions. So first of all, let's copy that, shrink the window, back to the Wolfram language, paste it, begin. Okay, there is the result. So you can see, let's magnify the font. Okay, so you can see here's the grid. You know, this is a graphics programming. So let's make it typeset. Control Shift N. Control Shift N. So you can see it's a typeset. You know, you can just press Control Shift N. So and watch as the windows shrink, they will be formatted in a smart way automatically. So this is fantastic, much better than LaTeX. You know, so Wolfram language. And okay, so here is the grid we just created, and then we just created the ball. You can rotate it. Then we just created this image. You know, we did a video of that last time. So that is a stereographic projection, and then there's a relation. In fact, the stereographic projection, you can see how it works. You just draw a line passing through a sphere. So any figure on the plane can be projected to the sphere, or vice versa. And so in other words, any points on the plane corresponds to a point on the sphere and vice versa. So you can, for example, the image on the plane can be a photo of you or someone else, you know, a photo of you or whatever, a house. Then you can project it to the sphere, and so it's very interesting. And you know, and then there's a relation. So to do the stereographic projection, you use certain formulas. For example, here is the projection formula, as simple as that. Okay, so let's see. We can, and projection works in any dimension. So let's just try it. Okay, so project, for example, x and y, you know, a point on the plane, and it becomes a point on a sphere. Okay, and actually, can this function do three? Yeah, it doesn't work for higher dimension, this function. But anyway, the idea can work for higher dimension as well. So anyway, you can see projection function is just a formula that takes a point, you know, two numbers, and return three numbers. Okay, these three numbers are the coordinates on the sphere. That's projection. That's called stereographic projection. Okay, now there's a connection between that and the geometric inversion. So for example, geometric inversion, again, it's also a function. That's very interesting. Okay, so we did the video of this. You can watch it. I recommend it. So it's beautiful. So essentially, it takes a point from a plane to a plane. That's a 2D case, or it takes a point from a three-dimensional space like here. For example, we start with a rectangular cage, and apply the geometric inversion of three-dimensional case. So it takes a point and returns another point. So the grid points of a cube becomes that. Okay, so that's the geometric inversion, three-dimensional case. Now, for two-dimensional case, it's similar. So for example, let's begin with a simple one. You start with a grid on the left, and you apply the function. Each two numbers, a point, gets a new two numbers. That's a geometric inversion, two-dimensional case. So you got the image on the right. So that's then we can use tubes to have more better visual effect. So we did that. So all these, and 2D case and 3D case, and here is another three-dimensional case. We begin with a bunch of cubes, then we apply the function and becomes that. So all these are geometric inversion. Okay, 3D case. So there is a connection between the stereographic projection and the geometric inversion. So in other words, before we used this projection function, to convert a point on the plane to a three-dimensional point on the sphere. That's the formula for stereographic projection. But because there's a connection to inversion, you can also use the inversion formula to arrive at the same answer. So in fact, the formula is going to be the same. So that is what we are going to do. Basically, we are going to do today is to create a pretty picture of the stereographic projection using the geometric inversion formula. Okay, so I'm gonna show you how it works in the mathematics aspect. Okay, and let me mention about Wolfram language. Okay, so if you just search for Wolfram language tutorial, XR Wolfram language tutorial, you'll find it. I did a lot of like 30 videos, 40 videos in the past 2 years. Lots of videos you can watch. And there's an introduction as well, Wolfram language, introduction to Wolfram language, symbolic computation and term rewriting system. That's this one, 2022, July 15th. That's a good intro, so you can read that. It's a term rewriting system. So Wolfram language is very different from all the other programming languages. Hello, guys. Hello, Nguyen. My pop out chat. Nguyen, my number one fan from 4chan. And hello, Louis. Oh my God, one sentence I did not understand. Well, it's very easy. It's very, very easy to understand. Actually. So, if you watched one of my video about the inversion, it's very easy to understand. Especially for programmers, because it doesn't involve. There's nothing. This is not math. This is, we are doing this, although it's a topic in geometry and mathematics. But actually, all you have to know is just, you can just ignore everything. Just know that there's this function that takes two numbers, return three numbers. That's projection. Projection is very easy to understand. Because you can just look at the graphics. Inversion is also very easy to understand. I explained before. Okay, let's get into it. So I want to show you. So here's the Wolfram language tutorial. So for you programmers, if you are, I know you guys have, are expert in JavaScript, in Golang, in Ruby, in Python. That's the domain of programmers. But the Wolfram language the Wolfram programming language is very different from all the others. It's kind of like Lisp. Okay, it's basically a Lisp. I did a video covering that. Wolfram language is exactly a Lisp. Like every concept about Lisp is the same in Wolfram language, including the nested paren syntax. But now there's a shortcut, so you don't see the too much nesting. But in fact, it is. I did a video on that. So anyway, it's a term rewriting system. So it's very very different from all the languages. The way you code it, is quite different, okay? And it's a functional programming language. So I want to show you here Wolfram language tutorial. Of course, I have everything, introduction, 30 pages. You can read that. But also, I want to tell you how to get it. So download Wolfram language for free. You can, go to this page and click download, and it's for free for personal use. What you get is a Wolfram Wolfram script and Wolfram engine. You don't get a notebook. Anyway, so I talked about that before, so you can just read it, or you can buy a Raspberry Pi. It comes with it free, the notebook, so it's fantastic. Okay, so that's the introduction, so you can download it and play with it. Now let's get to the let's see what we want to do now. Okay, so Wolfram language, so okay, so let me copy that and paste the link here, so we get a, so what is this? Okay, copy that, close that, paste the link. Okay, so here's today's talk show notes. Okay, so let's begin to code it. Okay, there's one more thing I want to show you. Just search for xahlee.info, and you click on Sali info search and XBOW. Okay, X-BOW. So Expose Keyboard Night. That's a keyboard I'm using currently, so it's fantastic. I recommend it. Okay, so so copy that, close it, back to Emacs. Well, back to that here, and paste the link here. Okay, so we have the notes. So let's begin coding this thing. So first thing, I want to explain what is the relation between this geometric inversion and the stereographic projection. Let's evaluate this again, so that you don't get grayed out thing. So we draw a ball and we draw the plane. Last time we didn't really finish the graphics, because what you really want is hold on a second. So you can magnify an image like that. Okay, so then you can see what we last time. Yeah, we should have drawn drawn the square, color it, and draw the line, projection lines. That way it's visualization. So when you see it, you understand it. Visualization is a very, very extremely powerful thing. So what we want to do is, we want to explain the relation between geometric inversion and this. So let me explain. Okay, so first of all, stereographic projection is very easy to understand. You have a sphere, you put a point from the top of the sphere, and you draw a line to any point on the sphere. It will intersect the plane, so that makes a association between a specific point on the sphere and a specific point on the plane. So in this way, any point on the sphere is connected to one precise point on the plane, except the top of the sphere. Okay, so in this way you have this association, this map. So this is called stereographic projection. Okay, so that's that. Now let me explain what is the geometric inversion. So again, we did the video on this multiple times, but let me explain. Geometric inversion geometric inversion is, again, in the 2D case is, so let me make a copy of this. Let's draw. And so geometric inversion in the two-dimensional case is that you have, so first of all, suppose you have a mirror, so you can understand a mirror. So a mirror, so you cannot do that here. So you have to open with snip and sketch. Okay, so if you have a mirror and you have a point, that mirrors here. If you have a point here, that mirrors here. So if you have a, let's say a triangle, and it becomes a triangle like that. If you have a square, then it becomes a trapezoid. A trapezoid becomes, trapezoid becomes trapezoid. That's a mirror. Everyone understand. Now, geometric inversion is actually just a mirror, but except a straight line, you have a circle. So given a, for example, given a axis, so you have a circle here with radius of 1. So geometric inversion is that every point outside of the circle becomes a point inside the circle. Any point inside the circle corresponds to one point outside the circle. So again, it's a map. So it maps the points inside the circle to points outside the circle. Okay, very interesting. So how is it done? How exactly is it mapped? In the mirror case, you just draw a horizontal line, and you see that's how they, each of the point map, the same distance. So mirror is a map in the plane such that for every point on the right side associates with a point on the left side and vice versa. That's a mirror. It's called reflection. The mathematical terminology is called reflection. Okay, so geometric inversion is the similar concept of reflection, except points outside the circle gets inside circle mapped to the outside. Okay, so the way it is exactly done is that you draw a line. Suppose you have a point here. Okay, so let's say this is P. You want to know which point this P corresponds to. This P will become inside the circle. So what you do is you draw a line from the center to this point P. Then basically the further the P is from the center, they become closer to the origin. So basically in this case, here is Q. Okay, so this P point Q, they correspond to each other. The closer P, let's say if you have a point here, let's say A, and that point will become here, B. You see, so the further away the P, the closer it becomes to the origin. The closer the P is to the circumference of the circle, the closer is the corresponding point. So just exactly just like mirror, okay? It's just like reflection. Like further away to the right becomes further away to the left. In the same way here, same thing. So let me show you. So we have, so close this, save it. Okay, save it. Let's open that. So let me show you. So there is a lot introduction on my website. Let's see, where is the link? Okay. So here is a page that explains the concept, the code, history, description. So you can click on this GeoGebra. Let me show you this very interesting application. So GeoGebra, so you can see here is the point P, and you can see the corresponding point Q. You see, so that's the geometric inversion. Now, if the point P is inside the circle, it's it just reverse. It's exactly the same thing. You see. So it doesn't matter where this point ray is. So this is a geometric inversion. And via this map, this function, this, given a point, two numbers, remember? So if you are a programmer, you can think of it just a function takes two numbers, returns two numbers. Okay, that's it. So via this inversion, geometric inversion, that's how you get all these pretty pictures, So here, for example, you have a bunch of blue circles, then you apply the geometric inversion, you get these kind of circles. Circle actually becomes circles. That's a very interesting property. Circles become circles, and lines also become circles. So here is many, various geometric inversion, and also there's a lot of applications, for example, in robotics, in mechanics, you want to convert a rotational motion to linear motion. You can build a mechanical linkage such that it does that. So for example, train wheels, locomotion, you want typically piston, they create rotational motion. You can turn it into a rectilinear motion. That's some of the application. Very interesting, and especially today in robotics. For example, you want to create a robotic dog, so how does the leg move? Well, that's via these mechanics linkages, so you can constrain the arms or legs to move only in a certain way. Okay, so that's the geometric inversion. Okay, so this is a two-dimensional case. Now, 3D case is the same thing. You start with a sphere. Any point outside the sphere becomes inside, and any point inside becomes the outside. Same thing by drawing a line. Okay, so so that's the geometric inversion. So now, what is the relationship, between how the geometric inversion and how the stereographic projection relate? Okay, let me explain that one. Okay, so let's make a copy. Okay, so let's do a screenshot, and let's open it in Sketch. Okay, so we can draw here. Okay, so here is how they relate. Okay, so in a stereographic projection, in 2D case, what we have is a line, and we have a circle above it. And suppose we want to know what is this point P correspond to. You start with at the North Pole, you draw a line to P, and this P, this line passes the circle here, so this point is Q. So in other words, a point on the line becomes this point Q on the circle. So this is a two-dimensional case of the stereographic projection, 2D case. Okay, simple. Now, 3D case, obviously, very easy. You can, it's similar. It's exactly the same. Now, so how does this relate to geometric inversion? So let me explain. So first of all, let's start easy with the 2D case, okay? Am I doing good? Am I doing good, guys? Say something, okay? Let me check my, good, fantastic. Mark says, North Pole, where is Santa? Okay, so let's go back to the so we want to, so here is a 2D case, 2D case of stereographic projection. Okay, so that is a 2D case. Now, let's talk about the two-dimensional case of the, you have to use the mouse. The two-dimensional case of the geometric inversion. Okay, so again, so let's review. So here is the, okay, let's 2D case of GEO inversion. Okay, did I spell it correctly? I forgot. S-I-O-N. Yeah. So in 2D case of geometric inversion, remember, you start with a circle in the center, and for any point P, you draw a line to the point P, and then it becomes a point inside. So this point is Q. Okay. Now, how does these two relate? It doesn't, at first it doesn't seem, they relate, because one is a point, becomes a point on the circle. The other one, the points outside the circle becomes inside the circle. So they don't, the only point that goes onto the circle is if you begin with a point on the circle. You see? So, but here is how they relate, okay? So here is how they relate. Very interesting. So if you want to do a stereographic projection, okay, so again, you start with a X and Y. So let's say, stereographic projection, you put a circle there, right? Now you want to know, so let's say this is a point P, and normally you would just draw a line to P, then you can see this point is Q, right? This is the normal way to do the stereographic projection. But now you can use geometric inversion to get this point Q. So, okay, the way you do that is this. You draw a bigger circle centered on the North Pole, so you got a circle like that. Okay, so you got a circle. So you want to know, so you see, you draw a big circle 2 times larger than the stereographic projection circle, okay? Now you do a geometric inversion with respect to this large circle. So now you can see this P and Q, they are actually geometric inversion now. So you see, so that is their relation, okay, between the geometric inversion and the stereographic projection, okay? So save it. And now let's start to code. Let's create some beautiful graphics. Am I doing good? So far so good? 3 people watching, okay. So let's start to code. Okay, so let's begin to code. We want to, okay, so start a Wolfram language. Okay, I'm coding Wolfram language in Emacs by this package Wolfram mod. Okay, so this is Emacs Lisp code that allows you to code Wolfram language in Emacs Lisp, and you can get it from this URL, and it's on GitHub. Okay, just search for Wolfram mod Emacs. You'll find it on GitHub. There's a download here, GitHub. Okay, so anyway, so we are coding it in Emacs, inside Emacs, because inside Emacs is it's much more efficient. You can, for example, I can type a matching bracket by, always type a matching bracket and so on. Close that, okay, close that, wait, don't close that, reopen. Okay, let's start to code. So now, how long I've been talking? 36 minutes. Oh my God. Hello, Nguyen. Fantastic. So now, what we want to do, let's do a fancy graphics first. So you see, this one is based on lines, okay? Now let's do it with tubes. Okay, so where do we go here? Wolfram mod. Okay, copy that, close it. Let's go back to talk show. Okay, paste the link here. Then we want to do cubes. Yeah, so cubes. What we want to do is now using these cubes. Okay, I mean tubes to represent those lines. So it will be beautiful. But before we do that, let me show you this one. You know, this is the power of Wolfram language. You see these graphics? How many lines is that in Python? Okay, in Wolfram language, one single line. Okay, copy that, go to Wolfram language, and let's just paste it there, and let's make it pretty. Okay, and let's run it. There it is. You see, fantastic. Fantastic, okay? And you know, this seems complex. It's functional programming, and it's a Lisp, and it's you know, it's actually much easier than you might think. It's a functional programming term. It's a term rewriting system. But let's not focus on that today. I mean, let's just do this. Okay. So we want to do this thing, but now instead of lines, we use cubes. Okay. Tubes, not tube. Okay, all we have to do is let's paste that. Okay, we're gonna modify this code. So actually, let's copy it. Let's go back to the Emacs here. Paste it. Yeah, here's the code. So very easy. Okay, so let's just. So I'm going to first of all not explain and just do it. Okay, it'll just be 2 minutes. Okay, so and show the result. Then maybe we can dive into how it works. So all we have to do is, so here is, you see here is the graphic 3D and graphics 2D that prints out the graphics. Okay, so all we have to do is just take that. Okay, take that, and here we want to do a replacement. Replace anything that has a pattern, just a line. We are doing pattern matching. Okay, that's what term rewriting system is about. You know, in normal languages, in Python, Ruby, you have regular expression, right? Regular expression, what does it do? Ultimately, you know, in a sense, it basically just do text, find and replace. It finds some text, you can replace it by some other text. And the way you find can be a pattern, can be, you know, a pattern that represents email address or a phone number, you know. So you can do find and replace with regular expression. And what is it, you know, and the regular expression is applied to strings, okay. That's a key concept of regular expression, the practical key concept, okay. You find and replace strings by a pattern. That's what regular expression is. Okay. Now, term rewriting is exactly the same. Term rewriting, but instead of string, you work on the whole language syntax. So what we are doing here is that we want to find any pattern that is the literally line. Okay. Then we want to replace it by. So you just type an arrow here, replace it by tube. Okay, that's it. Okay, and let's do the same thing. Let's do the same thing for the so for here and the whole graphics. Okay, it's just these two lines. Let's hope it works. Let's do it. I don't know if it will work, but it should. Run it. Fantastic. Fantastic. Yeah, it worked great. Fantastic. So I'm happy. Okay, so yeah, so that's it. That's it for, you know, as far as turning these lines into a cube. You know, the way it works, let me explain a little bit how it works. Okay, so well, the way this works, we already explained. We just do find and replace. You find, or all names in this, or in this data that is a line, literally line, you just replace by the tube function. So, and this works because line and tube, they have the same syntax. So for example, let me show you. So you look up the documentation for the line function. There it is. Let's magnify. Let's turn on JavaScript, and let's magnify. So here is line. So you just say line, curly braces, then inside it's just a bunch of points. Then it represents a line just like this. It represents a line in 2D or 3D, passing those points. That's as simple as that. Then you just slap on graphics, then it'll just print it. Okay, so for example, let's do a very simple example. So line, and let's say the first point is 0, 0. Now is this, so the first point and 0, 0 at the origin, and the second point is, let's say, 2, 3. Okay, so that represents the line. Then we can evaluate it in Wolfram language. It doesn't do anything because that's what it meant to be. It just represents the line. Now, if you want a graphics of it, just say, okay, graphics, then whatever above. Okay, so Control L to copy the input from above. Okay, so there it is. That's a line. And if you want the axis, X, Y, you can say axis true. Okay. Okay, so so now it shows axis. Now you can also show the grid. Let's see, grid. I think no, that's not option. So grid lines, automatic. Okay, so simple line. Now, if you want a three-dimensional case, very easy. You just add. So let's say from 0, 0, 0 to, let's say, 2, 3, 4, 2 points. Okay. That's incorrect. Okay, so because now you have a line where each point is a three-dimensional point. So you cannot use the graphics. You need to use graphics 3D, okay, to represent. So let's do it again. So there it is. This is a line. Now this option is no good. So let's remove that. Okay. So now what we want to do now, let's do tubes. Now tubes are exactly just like the syntax for the tube is and semantics of the tube is exactly just like line. Okay, so here's the documentation for tube, just exactly just like a line. The only difference is that it uses a tube to represent the line. Okay, so all we have to do is just let's copy that. Okay, so let's copy that. Okay, so these two things, now let's just replace line by tube. Okay, so let's just do it manually. So in Emacs, we can say find replace line by tube. Okay, do it. Okay, so except here is wrong. Okay, no, yeah, so there. So tubes, now let's run it. Okay, the first case is incorrect. Why is the first case incorrect? But the second case works. 3D. Oh yeah, it doesn't work for the first case because the first case is a two-dimensional case. Now the tube can only be used for three-dimensional. That makes sense because it's a three-dimensional thing. Yeah, so but the point here is that you see it's exactly the same. You see now it's a tube, and before it's a before it's a line. Now we can add thickness to the tube by just add a second argument. Let's say thickness 0.2. Okay, do it. Now you see you got a thick cube. So the point here is that the tube function is exactly the same as the line function. The syntax is exactly the same. So you can simply replace any line literally just by tube, then you'll become tube. So that's how this works. Now the replacement we did here is manual. We manually did find replace, but you can do it programmatically by, for example, so here's a line. So let's make this pretty. So typically in programming languages you format it this way. In Wolfram language, you don't do that. You don't do, where I need a tab here, tab. Should it be space or tab character, or how many space represent a tab, like Python, idiotic fuck. In Wolfram language, you don't do that. In fact, the whole thing, for example, the whole thing can be just a single line. Let me show you, okay? Normally, you don't format at all, so make the whole thing a line. That's valid code. Copy that, paste it there. It's invalid. Why is that? I did something. Oh yeah, it's invalid because I forgot. Wait. I forgot to add semicolon. Okay, so you need semicolon here. Let's add semicolon. Here, 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 here. Okay, now let's put the whole thing into a line. Okay, copy it, paste it. There it is. Oh yeah, when you put semicolon, it suppresses the output. So you don't. So you don't want the semicolon at the end here. Okay, so you can see. Now you can see they automatically format in a smart way as you adjust the width, the window width, or as you type. That's the power of Wolfram language typesetting, okay? And you can press a key, Control-Shift-N, it becomes typeset, okay? So again, you see, this is supreme, okay? So that's an advantage of Wolfram language. That's why I love it. I've been coding it since 1992, far more advanced than the industrial coders, the industry, coding community, C, C++, C#, even Haskell. They have nothing like this. And then the industrial coders, they don't understand. They've never seen this before. They kept, they have idiomatic guide, Python idioms. They tell you how you should, manually format or configure your Emacs. It's very complex. So this is a power. So anyway, so now we got this. So we can programmatically replace the line by tube by just this syntax. So let me show you what this means. Okay, so let's this code, this line, let me just paste it. Okay, so this code can be written in a more nested way by like this. Okay, so let me do it. So you just say replace all. Okay, so replace all, then two arguments. The first thing is the thing you want to replace. That would be export. Okay. The second thing is the thing you want to find and the thing you want to replace. That is represented by a rule. Okay, like that. Wait. Okay. So the rule takes two arguments. The first thing is the find pattern. The second argument is the replace pattern. So the find pattern is gonna simply be a line, literally, and the replace pattern is simply gonna be a tube, literally. So now we don't need this part anymore. So you see. So now remember, this line, that's a syntactical shortcut. Okay, is exactly the same as this line. Here is where you see it's fully nested. There's no special syntax like the C for loop, while loop, I plus plus. There's no special thing like that. Everything is purely nested, just like Lisp. In fact, more regular. So this is one of the reason Wolfram language is, it's a Lisp. It's basic. It is a Lisp. It's derived from Lisp and APL, programming language. Okay. So anyway, we got this, and let's run it. Okay. Do it. You see. And now, if we remove those, let's change the tube to line. So it actually doesn't replace anything. I mean, if we do this, line becomes line itself. So it doesn't effectively, it does nothing. Okay, so if we do this, then it's just lines. Okay, so I think I love using C++ work. Very good at Office, my friend. Okay, I think that's it for today. 50 minutes. Yeah. So, that's it for today. Thank you for watching. If you like my stuff, donate. Okay, Patreon me, PayPal me. You can go to my website xali.info. And lots of interesting things, and at the bottom, Patreon, Amazon gift card, PayPal. Okay, thank you guys. Okay, we shut down in 1 minute or two. Any questions? Any questions you find interesting, you want me to explain, or anything? Okay, so here is today's code. It's fantastic. Yeah, we demonstrated this. Basically, some aspect of the term rewriting system. You see that, what you are looking at today, what we did today is actually that's one of a very good example of term rewriting power. In other languages, you can't really do that, and this part of the power came from, for example, in Haskell, in OCaml, in F#, in the functional languages, or today even in Python and Ruby, you have some form of pattern matching, okay, which is similar to what we are doing today. But however, the Wolfram is the real term rewriting. Why? Because the difference is that the Wolfram language term rewriting, pattern matching term rewriting, it's a symbolic. Okay, so it's just like Lisp. In Lisp, every variable, every function name is actually a symbol that stands by itself. It's not just a byway to a value. It's actually a symbol. So you can manipulate all these symbols symbolically. Okay, so in Wolfram language, combined with pattern matching and replacement, like we are doing today, replace all. So what you become, so it becomes a term rewriting system. Effectively, what it means is that every syntax is just a sequence. It becomes like a string. So so when you want to do computation, you are just doing find and replace by a pattern. for the whole language. So in other words, you can think of, for those of you Lisp coders, this is Lisp macro, okay? Lisp macro, but with a magnitude more power. So the whole language, that's the fundamental way you do computation in Wolfram language, is term rewriting, okay? So essentially, every computation you do is just finding some pattern and replace it with another, sequence of symbols, and do that again and again and again and so on. In fact, when you define a function, the way function works is that you just define a pattern. So whenever Wolfram language found that pattern, it just replaced that pattern by the function's body, and so on until no rule matches. So that's the essence of term rewriting system. Okay, thank you guys for watching. That's it. Bye, guys. So you're gonna close this. So let's pop the code back to so let's clean up this. Okay, syntax correct, show in browser. That's what we talked today.